In this demo, we'll take a look at high availability options for SQL Server running on a container platform. And this applies to Kubernetes or variants of Kubernetes like OpenShift. In today's demo, I'll actually show you running on OpenShift on Azure, which is a new managed service that Microsoft and Red Hat jointly announced at the Red Hat Summit this week. Now, if you want to do this today, your option is to deploy sort of a failover cluster instance model on Kubernetes or OpenShift. And we've documented this and publicly up on the public documentation for SQL Server on Linux, and we officially support this pattern. So in this pattern, you would deploy a SQL Server container onto a Kubernetes node as part of a pod. And you would also typically create a service that points to that pod and then have your applications connect to that service. And then you would definitely, in almost all cases, want to have your data persisted on some sort of persistent volume claim. And in this case, especially, that's important because we need to have shared storage where each of the pods can access it if we need to fail over, for example. So in this example, we would mount the directory var opt ms-sql where the data files are stored at to some persistent volume claim on remote storage. Then if the pod for some reason fails, then Kubernetes will automatically redeploy a new pod. The service will be updated to point to that new pod, and the pod will mount back to that same persistent volume claim where it can see the data files that are stored on that shared storage, and it will recover the database using those database files that exist on that shared storage. Now, if the entire Kubernetes node were to fail for some reason, then Kubernetes would deploy a new SQL Server pod on a different node. The service would be updated, and the pod would just use that same persistent volume claim to mount to shared storage. And in this pattern, it's very similar to the failover cluster model that you might see using something like Windows Server or even Pacemaker on Linux VMs. Now let's take another option where we might want to deploy always-on availability groups on Kubernetes or OpenShift. And this is an interesting pattern because it gives you the flexibility of having either shared storage if you want, like remote storage that's shared, or you could even have local storage, which might give you a better option in terms of your storage performance. And that's because with always-on availability groups, the data is replicated across n number of instances of SQL Server, and each copy of SQL Server has its own copy of the data, and that data can be stored either locally or on remote storage. So in this pattern, we first deploy an operator, and the operator is used to orchestrate the deployment of an always-on availability group and manage the lifetime of that availability group on Kubernetes. Once you deploy the operator, you can then, through that operator, deploy an always-on availability group, which will deploy a stateful set per each of the nodes that you want to have a SQL Server running on. And you can decide how many of these stateful sets you want. Typically, you would see maybe a three-node always-on availability group cluster. Each of those nodes would get its own stateful set. And within that stateful set, you would have a pod. And within that pod, you'll have two containers. One which is a SQL Server container, and the other which is an availability group agent container, which is there for monitoring the availability of the SQL Server container that it's in the same pod with. And then if it detects that there's some lack of availability of that, then it will communicate with the other agents that are in the same always-on availability group to do leader election and then orchestrate the failover of the availability group to a new primary. Now, lastly here, you'll have a service that your applications will connect to. And the service will redirect all of the connections to whichever pod is currently the primary. So let's take a look at what this actually looks like running on OpenShift. So here I am, I'm at the terminal on my MacBook here, and I'm just going to run OC get pod. And this will reach out to OpenShift and it'll get me a list of all of the pods that are in my environment. And you can see here that I have this SQL 1, 2, and 3 pods. And so each of these pods has a SQL Server container running inside of it, and there's also an agent container running inside of there. So if we want to take a look at what that looks like, we can just pop into our OpenShift UI. So inside of the default project here, we can see the different pods that we have available. We can pop into one of these pods here, and you can see that there are two containers, one which is MS SQL Server, and the other which is AG Agent. Now, let's take a look at something else which is interesting. We can run this command here, which will go and get the JSON information about the particular pod, where the pod has a label on it that it is the primary. And so we can see that right now SQL-2-0 is the primary pod, and all application connections are going to that particular pod. Now, I've created a simple .NET application that runs inside of a container. So I'm going to OC delete pod. I'm going to delete this pod so that it starts a new one for us. And if we just go into the OpenShift UI here, and we go and look at sort of the pod I just deployed to this application, we can see that this application just outputs to the terminal in a loop which SQL Server instance is connected to. So as you can see right now, because this container is connecting to SQL Server through the service, and the service is routing the connection to whichever pod is labeled as the primary, right now this application is outputting that it's connected to SQL-2-0. So what happens if we delete that pod? So we'll just kind of simulate a failure of that pod by just simply deleting it. So we can do delete pod SQL-2-0, which is the primary right now. And if we delete that pod here as we do OC get pod, we'll see that that pod will now be marked in the terminating state. And the next time we run this command here, we'll see that the SQL-2-0 pod will still be the primary for now because it's terminating. But if we just kind of keep running this command, we'll see that at some point there won't be a pod labeled as primary. And now the agents have talked to each other and they've elected a new leader. And so the new leader is SQL-3-0. And we can see here in our application that our application lost connectivity for a period of time there, but has since resumed and is connected to SQL-3-0. And this application just simply connects to SQL Server every 1 second. So we can see that we lost connectivity for about 6 seconds before we were able to resume connectivity over to that new SQL Server instance that's now the primary. So very fast failover times because we have multiple instances of SQL Server that have a replicated copy of the data, and we can just simply make one of them the new primary. The other great thing about using something like Kubernetes to manage your orchestration of your containers is that Kubernetes will automatically redeploy that pod that was deleted. And once that pod comes back, it will automatically join itself back into the always-on availability group as a secondary, and all of the data will be automatically replicated back over to that new pod, unless you're using persistent volume claim, in which case it'll just remount to that persistent volume claim. The data will already be there, and it'll simply catch up to whatever the latest data is from where the primary is at. So if we now run this OC get pod here, for example, again, you'll see that SQL-2-0 is already back and running. So thanks for watching.